talk a little bit about the variational description of Einstein theory, about Einstein-Hilbert action, in general covariant actions, and then talk about conserved energy and momentum. Okay, so first I want to discuss the action, the variation description of general relativity, and I want to start by making an analogy with electromagnetism. So let me try to divide this into two parts and see if I can make some parallels. So here I draw a line, and then we zoom in. Well, maybe I didn't need a line. Okay, so first we want to talk about E and M and review some stuff from the E and M. So in particular, I want to talk about the idea of gauge invariance and gauge transformation in electromagnetism in Maxwell theory, and see how there is an analogous concept in the case of GR, and that would be a guiding principle for constructing the action for a gravitational theory, matter coupled to gravity. So in electromagnetism, originally when we first learn it, usually it is formulated in terms of E and B fields. Like we get the Maxwell equation, which in the modern language looks like F mu nu equals J nu. So this is fully in terms of the field strength F mu nu, which is itself related to E and B fields. Like F0i's are the components of the electric field, and Fij's are the components of the magnetic field. However, we introduce the vector potential in the following way. And once we define it in this way, we realize immediately that there is an invariance if we change a mu by a total derivative. So if we change a mu by a total derivative, F mu nu doesn't change. Therefore, the Maxwell equations do not change. So this is a redundancy of this description. So this is a redundancy of description, or which we also call it gauge invariance or gauge symmetry. Now, at this level, it might look a little bit unnecessary to introduce this vector potential. So for instance, one useful fact about it is that it's a little bit more economical to work with a mu rather than f mu nu. At least superficially, it looks more economical because there are 6 in, so in d equals 4 is 3 plus 1 dimension. There are, so f mu nu has 6 components, while a mu has 4 components. So this looks a bit more economical. However, it's not just a matter of being economical to use a mu field. It's actually it's actually more important to switch to this language in terms of the vector potential. And we can see the example of that in the case if we consider the following experiment. So if we have a solenoid with a magnetic field, so there's a magnetic flux inside this solenoid, but outside there is no magnetic flux, then we know that there is the Bohm-Aharonov effect, that if you have if the wave function of the electron can go around this solenoid, then it will feel the existence of this magnetic flux. So there is, or Aharonov Bohm. Aharonov Bohm effect. So if you have this electron going around this solenoid, will feel the presence of this magnetic flux. Now, if we want to describe this effect in terms of local physics, if we don't want to go and search the whole space or the whole region that this away from the, so you can imagine this electron path can be very far away the location of this solenoid. The only necessary condition is that they go around it, but they can be very far. So we could describe this Bohm-Aharonov effect, or the phase that we gain by going around the solenoid, but in terms of the vector potential, right? So an integral of a mu dx mu times the charge of the electron E, that would give us the phase shift that we gain by going, or phase difference of the two paths. So this will be delta phi. And this is a completely local description of the local way of deriving the phase that we gain. By local, I mean I'm just integrating something, in the along the path of the electron. While if we wanted to describe it not in terms of the vector potential, but in terms of electric and magnetic field, there wouldn't be any magnetic field outside of the solenoid. So we had to be careful about the fact that this path is actually going around the solenoid. So it would be, wouldn't be able to write some local expression. Local meaning that something that just is given in terms of the leaves in along the trajectory of electron that gives delta phi the phase. So So the real usefulness of a mu is that it allows local description. Now, more perhaps more um, uh, um, more useful, important, or more universal is the fact that if now we talk about field theories, and or in particular quantum field theories, which we know is the way to combine quantum theory with the special relativity. If we talk about quantum field theories, then the way we describe them is that so when we talk about field theories, we describe them in terms of an action and use the variational principle. So we have some action S of some fields psi. So this psi just describes the collection of all fields that we might consider. We write an action which is an integral over some scalar quantity, and we do the variation of that to get the equations of motion for the fields. Now, if we have fields that are charged on the electromagnetism, then if we want to also give a variation or description for this theory for the electromagnetic field and charges or fields that are charged on the ENM, then we need to use the vector potential. And we should write an action in terms of this vector potential which satisfies this principle of gauge invariance or gauge symmetry. So in other words, the prescription would be that we write an action such that if we do a transformation of the charge field, so if we imagine this psi field is a charged scalar field, we charge Q, and we do a transformation, infinitesimal transformation of this psi field. And similarly, do U1 transformations for other charge fields according to the charge and the transformation properties. And at the same time, we transform a mu then the condition of gauge invariance, the principle to construct this action S, the principle that we follow is that delta alpha of S has to be equal to 0. Or in words, we construct a local gauge invariant action. So here the use of a mu, the vector potential, is not arbitrary. It is actually necessary for having this local description, variational description. Okay, so now, so this was the story about the electromagnetism. Now we want to go to the case of gravity. Okay. So we want to make a parallel and go consider gravity. Is there any question about this part? Now I want to make an analogy and discuss how we would construct an action for a theory of gravity, which is going to be a general covariant action. And the rule for constructing that action would be similar to the rule that here we had for constructing the U1 invariant action. We just impose a different gauge invariance principle on the action and then write the local action that satisfies, or the most general local action that satisfies that condition. Questions? Okay, now we want to consider the case of gravity. But before talking about gravity, let us first just talk about the general laws of physics that we write in classical physics before talking about gravity or general relativity. So say in Newtonian physics, we write laws of physics that usually almost always they refer to some coordinates. Say for instance, we write F equals ma, which talks about the position of a particle that is moving. So we are picking some reference frame and then write, for instance, F equals ma, where a is the second derivative of the position of the particle with respect to the absolute time of the Newtonian physics. So here, of course, again, we are everything is referring to some choice of coordinates. Now, what happens is that, so here is, I shouldn't really call this gravity for now. It's just we want to discuss what coordinate system or reference frames. Let's give the title reference frames. So what happens is that in classical physics, like in Newtonian physics, or even in a special relativity, we have preferred reference frames in which we write the laws of nature. So there exists preferred reference frames. There is no unique reference frames. There are infinitely many of them, but for instance, in Newtonian gravity, they are related by Galilean boosts, and in special relativity, they are related by Lorentz boosts. So we have these inertial frames in, for instance, relativity, and there are Lorentz transformations that relate them to each other, and we have simple forms of the laws of physics in terms of those frames. Now, if we want to transform to other reference frames, we just take the laws in these preferred frames and then carefully change the variables to the new coordinates. For instance, we can imagine trying to go from the Cartesian coordinates. So these Cartesian coordinates are the preferred coordinates that we use when, for instance, we write the second, the Newtonian laws of dynamics. So if we, for instance, want to go from Cartesian coordinates to curved coordinates, like a spherical coordinate, in general, curvy linear coordinates, meaning that we want to go from X and Y and Z to, say, for instance, to R, theta, and phi, what we can do is to just take the original set of equations and then see what is the relation between X, Y, and Z and R, theta, and phi, and then plug it in the equation. You get some new equation that look kind of different. And then for any new choice of coordinates, we can repeat this to get the new laws. But there is a perhaps, again, more economical way of doing it, which is to use the variational principle and use the Lagrangian formulas. So if we use a variational principle, then there's a relatively simple recipe for finding the new laws of nature in general coordinates. What is that? If the laws of nature follow from the variation of an action, so we have, say, for instance, in this case, we write an action for X, the position of the particle. Or if we are working with some field theory like Maxwell theory, then we have some action for a set of fields. So now I generally denote those fields with psi, but this psi can be any field, could be the Maxwell field. Then and these are actions that we can construct, for instance, by constructing on that preferred frames. But then the rule for generalizing it or deriving the equations of motion on curved coordinates is that construct actions that nullly depend on a metric with the condition that if I set the metric to the Minkowski metric, for example, to the flat metric, then the action reduces to the original one. So if G mu nu, so now I'm considering particular example of just a relativistic theory, but similar statements can be made also in the non-relativistic. So if G mu nu is eta mu nu, if we use go back to the preferred Lorentz frames, then the action reduces to the original one. Moreover, it has a property of general covariance, meaning that if I change the coordinates x mu, make an infinitesimal transformation of the coordinates, under which, for instance, a scalar field changes by xi mu d mu psi. Now, psi is a scalar. And then similarly, we have similar transformations of vector and tensor fields. And moreover, if we transform the metric G mu nu by minus del mu xc mu minus del mu xc mu, then under these transformations, delta xc of the action is equal to 0. So we construct the action with these two conditions. And this second condition is called general covariance. So this is a general covariant action. Okay, I just write covariant. So if we do that, then we automatically get the equations. If we vary this new action, which was constructed with these rules, then variation of this new action, it automatically gives us the correct equation of motion on any coordinate system. Of course, we didn't have to do it. We could just work with the preferred coordinates, and if we needed the equations in the new coordinates, we could just do the transformation at the level of coordinates. In Newtonian physics or in special relativity. However, once we go to general relativity, then Einstein tells us that there is no preferred reference frame. So globally, there is no preferred choice for this, at least generically. Maybe in some particular situation, there is preferred frames, but generically, the space-time, the metric is dynamical, and there is no preferred choice for it. Therefore, once there is no preferred choice, we have no choice but working with this generally covariant action. There's no alternative. So in Einstein gravity, there's no preferred reference frame. Therefore, we the laws of physics have to be generally covariant. Okay, so then the question would be, what are the exact rules for constructing this general covariant action? So I mentioned some of them here. Like we basically decompose fields in terms of the scalars, vectors, tensors, in terms of the transformation properties on the coordinate transformations, and then we construct local actions so that if we apply general coordinate transformation, the action doesn't. This in particular means that, for instance, if we have the derivatives, maybe I should have said it here. If you have derivatives, those derivatives have to be replaced by covariant derivatives. And for instance, if we have, so maybe, if we have the volume integral, now this volume integral should be, or the integral over space-time now has to be over, we have to use a measure that is invariant on the change of coordinates. So normally we write the action as an integral d4x of some L, some Lagrangian of psi. So this was an action. This was an action for a field psi, and this action goes to S of psi and G mu nu, which is written as d4x square root of minus G times some Lagrangian that depends on psi and G mu nu. Where now this the property of this measure is that under coordinate transformation, this is invariant, so this goes to d4x tilde minus G tilde, and that L is the scalar quantity. So let me just give some examples. But before that, is there any question? If I can draw the line. Okay, if there is no question, I'll give just a couple of examples. I imagine that you are already familiar with constructing scalar quantities out of vectors and tensors. And these are the same rules that we are following here. So for instance, in the case of Klein-Gordon theory, the Lagrangian, we have the Klein-Gordon Lagrangian, which depends on the field phi and g mu nu in the following way. Notice that my choice of sign is depends on the signature of the metric. So you might have seen the first term with a different sign. And that is because that was written in a different signature. So as you see now, I have written the Klein-Gordon Lagrangian in a generally covariant way. So this object, this Klein-Gordon field is a scalar field. So this part is a scalar field. Since phi is a scalar field, the covariant derivative of phi is the same as the covariant derivative of phi is the same as the ordinary derivative of phi. So therefore, here I could just write the ordinary derivatives contracted with the metric, and so that's it. This is a scalar quantity on the coordinate transformation. Now, similarly, if we want to consider the Maxwell theory, so here, let me see how to. Let's put this there. Examples. So if now we consider Maxwell theory, then we have L, E, and M is equal to minus 1/4 G mu nu G alpha beta F mu alpha, F nu beta. Perhaps you have seen this action before in QED, except that maybe not with the general metric, but with the Minkowski metric. So the rule here is that now we replace the Minkowski metric with the general metric, and then F mu nu, which normally we would write it in terms of ordinary derivative, now we write it using the covariant derivative. Although actually in this combination, it doesn't matter. So again, this F mu nu that we construct is a second rank tensor, and this object that is written here is a scalar quantity. And once we plug it in that action, we will get a generally covariant action whose equations of motion will be valid on arbitrary spacetime. Okay, so this is the rule that we follow in general relativity to construct an action. Now, let us see one particular consequence of this rule, which is interesting because it gives us now a prescription for deriving the energy momentum tensor, even if we are not talking about gravity. So we said that because in gravity there is no preferred frame, we just have to, in that case, we just have to work with general covariant theories. Now, even if we don't have to work with them, it's sometimes useful to work in a general covariant formulation using a general metric instead of restricting to flat space. So let us discuss talk about energy momentum tensor. Energy. But before that, let me just ask if there is any question at this point.
Yes, Professor, just a simple question.
Yes?
In the Klein-Gordon Lagrangian, do we have a negative kinetic term?
You mean here?
Yes.
No, this is, so this expression, let me do the, so this minus sign is perhaps unfamiliar because you might have seen it with a plus sign, but that depends on the choice of the signature of the metric. Depending on whether you work with mostly plus signature or mostly minus signature, then you would put a minus sign or not in here. So this is, since I'm working with mostly plus signature, then there is a minus sign. So for instance, if we look at the, so how do we determine whether there is a negative kinetic term or the kinetic term is a standard? Let's go back again to the case of Minkowski. So imagine G mu nu is equal to eta mu nu. And therefore also G mu nu covariant, the inverse G mu nu is also equal to the inverse eta mu nu. Then in my signature, this eta mu nu is minus 1, 1, 1, 1, which means that if I look at the 0, 0 component of this, the 0, 0 part of this term, well, let me write the whole thing. So this term will actually look like 1/2 phi dot squared minus the spatial derivative of phi and the squared. So it is a standard kinetic term. Any other question? Okay. So yes, we want to imagine we construct a general covariant action. Now, so what does it mean? If I have a general covariant action, it means that delta xc of S, which depends on some matter fields. Again, this size, this stands for the collection of all matter fields that I have. And G mu nu is equal to 0. So this is just the statement of general covariance, which you should think of it as being the analogous of the gauge symmetry that we impose in electromagnetism. So remember there we said that we construct an action and we require that it is invariant on there. Let's go there. We construct an action and say that it is invariant on this transformation, this U1 gauge transformation, which had one arbitrary parameter alpha. Now the analog of that is this xi mu. So now we have 4 parameters. So it's a much bigger symmetry group that we are requiring the action to be invariant on. Yes, so now we have constructed, imagine we have constructed a generally covariant action. Like for instance, in these examples, following these rules, we construct a generally covariant action for the Coulomb-Gordon field or for the Maxwell field. Then we can go and ask the following question. So it is generally covariant. Let us apply this to the action and see how we can derive a covariantly conserved energy momentum tensor using this construction. So we just take this inside the action, this variation. So I have integral d4x. There will be the variation of the, I have the Lagrangian. There will be 2 terms. There will be delta xc of psi, the variation of the Lagrangian with respect to the psi field. So now I drop the arguments. And then there will be the variation of the metric times the variation of the square root of minus g times L with respect to metric. Okay, so this is just the general transformation rule that we have. Now let me a little bit analyze this term, the variation with respect to the metric. So first of all, the change of the metric delta xc of g mu nu is minus. So we're focusing on this term. So it's minus del mu xc nu plus del mu xc mu times delta of the square root of minus gl delta of g mu nu. Since g mu nu is symmetric, this is just twice one of the terms. So we get minus 2 del mu xc mu delta of the square root of minus gl delta G mu nu. Okay, so now let us write this in the following way. So I can multiply and divide by a square root of minus G to get the square root of minus G del mu xc nu minus 2 over the square root of minus G d square root of minus G d G mu nu. Now we had an integral d4x of this term. Right here, this term was inside an integral. So I want to do an integration by parts. So if I do an integration by parts, what I will get is d4x square root of minus G del mu of x in mu minus 2 over square root of minus G. Oh, actually, I want to give a name to this term so that I don't have to write it always. So let me remember what is the name. So the name of this term, we want to call it, actually, let me also erase this minus sign, put it there. And then this term that we have here, I want to call it T mu nu. And then you will see why I call it T mu nu. So if I do that, then I get minus, because I kept the minus sign, del mu, T mu nu. And then there will be there will be a second term, which is x nu del mu T mu nu. So this expression, or minus this expression, is just what I had before. I haven't done anything. If we take this derivative inside, then this term cancels, and this derivative acting on xi reproduces the original. But now this first term here is a total derivative. So the first term can be written as so here we have minus integral d4x, and the first term can be written as d mu of the square root of minus G x nu T mu nu minus the second term, I keep it as it is. And now we remember that this xc was arbitrary. So general covariance is the statement that for any xc, this variation has to be 0. This is like the gauge invariance in the U1 case, that alpha parameter could be anything. So similarly here, this xc could be anything, any infinitesimal thing. So in particular, xc can vanish at infinity. In fact, normally we are interested in those xc's which vanish at infinity, which means that this term, or they have a local support anyway, if there is no infinity, which means that this this term is 0 for those choices. So xc mu take x mu to be localized. And then as a result, this integral of this first term will be 0. Okay, so then we'll end up with the second term. So there will be the second term. And now let me put it back together with the original part. So what we will have learned is that the change of the action, which was 0, because it was generally covariant, is equal to integral d4x delta xc of psi delta of square root of minus gl delta psi. So I have two minus signs, it gives me plus and plus the square root of minus g. And here I forgot a factor of x in nu, right? So here we'll have the same thing. I'm just copying the same thing. X in nu del mu t mu. So this expression is equal to 0. This expression is always 0 for any choice of x in mu. But now let us imagine that we take this and, oh, by the way, again, since x in mu is arbitrary and localized, it means that this object has to vanish locally. So this expression is just 0. Or it's a total derivative. It doesn't have to be 0, but it can be a total derivative. Now, let us imagine that the matter fields are on shell. If the matter fields are on shell, then this term will vanish, because this is just the normal variation of the action with respect to the matter fields. And we know that the variation of the action with respect to matter fields, it gives matter equations of motion. So if the matter equations of motion are satisfied, which is the definition of being on shell, then this first term vanishes. So this term is equal to 0 on shell. Well, on shell means equations of motions matter equations of motion are satisfied. Since the whole thing has to vanish, and since xc is an arbitrary function, can be localized at any point, we conclude that del mu t mu nu on shell is equal to 0. So that's why I called it T mu nu, because I constructed a rank 2, a symmetric rank 2 matrix, which is conserved on shell. So this is a natural candidate for the energy momentum tensor of this matter fields. And let me just remind you that this T mu nu is defined in the following way. Now, this is something that I use interchangeably. I sometimes write the variation of this combination in this form, and sometimes write it as the variation of the action, but this, I mean the same thing. It means that we replace that that function by delta function, and then and times an infinitesimal, and then you do the usual variation. The same way that we do variation with respect to the fields to derive equations of motion. So that's how Timmy knew, or that is now a new definition of Timmy knew the energy momentum tensor that we can, for instance, check, say in the case of Klein-Gordon theory. So say if we take the example of Klein-Gordon theory, where we can easily also use another procedure or another theorem to derive energy momentum tensor, you can see that this definition that I give here is gives an equivalent, it gives the same expression for T mu nu. Right, so how do we check that? We know that the Klein-Gordon action is integral d4x square root of minus g times minus 1/2 g mu nu d mu phi minus 1/2 m squared phi squared. Now we want to do the variation of this action with respect to g mu nu. So let's say if I want to know T mu nu with lower indices, that will be minus 2 over square root of minus g delta S Klein-Gordon divided by delta G mu nu, because the variation of the inverse metric is minus the related by minus sign to the variation of the metric itself. So if I do these variations from here, I will get d mu phi, and then from here, by varying the square root of g with respect to inverse g mu nu, I get so delta of the square root of minus g delta g mu nu. It is minus 1/2 g mu nu times the square root of minus g. So if I use this, I will get minus 1/2 g mu nu times yes, so I have the minus with minus cancel, so I have a plus, and then I had another minus sign there. Okay, so it becomes minus. So I have g alpha beta d alpha phi d beta phi plus m squared phi squared. Now here we can, one thing that we can do is that we can set again g mu nu to eta mu nu, and what we get is the original, or the, perhaps you have seen the expression for T mu nu of the Klein-Gordon field that follows from doing the Noether procedure. Okay, then now we can also, you can do other exercises, like you can apply to the Maxwell theory as one of the homework problems asks. So, okay, so now, so what we have learned is that we construct the general covariant action, then there is an alternative way of deriving energy momentum tensor generally symmetric, conserved, covariantly conserved energy momentum tensor, and that is by varying this general covariant action with respect to the metric, like we did here. All right, but this now, of course, if it is just a tool to find the T mu nu and then setting G mu nu to eta mu nu, then this conserved energy momentum tensor is useful for finding a conserved energy, right? Because so if so let us talk about conserved or conservation laws. So if G mu nu is equal to eta mu nu, then what happens is that this covariant conservation, by the way, I can always lower this index because the covariant derivative commutes with the metric. This will go to ordinary conservation. And we know that when we have ordinary conservation, from that we can derive conserved charges in general. Or in this case, we can derive conserved energy and momentum. How do we do that? When we can define P mu as the integral over, so now we are in Minkowski, or we are assuming that we are in Minkowski, so we can take a spatial slice and integrate the zeroth component of this energy momentum tensor over a spatial slice, and that gives us a conserved quantity. Why? Because if I take the derivative of this P mu with respect to time, which is x0, that is integral d3x, which is integral over x and y and z, the spatial coordinates, that becomes d0 of t0 mu. But because of this conservation law, I can write this as minus integral d3x di ti mu. And this is a total divergence, so reduces to boundary term. So if you are integrating over the entire spatial slice, this will be an integral over the boundary of ti mu. So will be 0 if there is no flux at infinity. So that's how we derive conserved charges, assuming that there is no flux at infinity, and when we have an ordinarily conserved current, then from that we can derive conserved charges, in this case it becomes 4 of them, which we can call the energy and momentum. However, on general generically, on a curved manifold, on curved space-time, this step cannot be done. We have a covariantly conserved T mu nu, but that does not mean that there is any quantity which is ordinarily conserved. And without having an ordinary conserved quantity, we could not follow these steps. So here it was very important that we have an ordinary derivative, not a covariant derivative. So therefore, on curved spacetime, generically, there is no conserved energy and momentum. There is a covariantly conserved energy momentum tensor, but there is no analog of total energy. Maybe I should say, emphasize. There's no conserved total energy and total momentum. It doesn't really make sense to talk about the total energy of the space-time or the total energy of the matter fields in a space-time or the total momentum of matter fields in a space-time in general. The reason, maybe the more physical reason for this is that, so this T mu nu that we constructed here, it was constructed out of the matter action, right? So here, let us go back to the derivation. Here, this S that I consider here was just the matter action. So maybe let me put this. So this S had to include all of the matter fields because, of course, we can imagine the matter fields that are completely decoupled from each other. And then they would have independently conserved energy and momentum. But once I couple matter fields to each other, then there will be only a single conserved energy and momentum for those matter fields. So this S was the action for the matter fields that I had here. And therefore, this T mu nu that I defined here, that was the energy momentum tensor for the matter fields. However, in a gravitational theory, you have seen that we have, for instance, gravitational waves that carry energy and momentum. So it doesn't make sense to expect, we shouldn't even expect to have conserved any energy and momentum just for the matter fields, because the energy and momentum of matter fields could be transferred into the gravitational waves. So this is perfectly natural that there is no concept of total energy and total momentum that can be defined just from the T mu nu of the matter. Okay, any question so far?
I have a question.
Yes?
So in our case, the action we considered, is this action invariant under global translation symmetry? I mean, global translation? I mean, if there is a symmetry under global translation, so then we obtained the canonical energy momentum tensor, which is conserved. So does it mean in our case, there is no global translation symmetry?
So let's see, what does it mean to have a translation symmetry of the action? It means that you don't have explicit dependence on the coordinates, right? The dependence on the coordinates is just inside the fields.
Yeah.
Which is true. We don't have explicit x mu dependence in the action. However, so therefore, I guess what you are proposing is to apply the Noether procedure, the Noether theorem to this action. Yes, we can do that, except that Yeah, I should think a bit about it, but I think the answer that you will get is that if you apply the nodal procedure to a general covariant action, you will get 0. But let me think about it and tell you.
Okay.
Any other question?
Yes, I have a question too. So here so far we only consider the matter fields,
Yes.
and then to put a total, an overall action, don't we have to also put the fields concerning the gravitational waves?
Yes.
And in that case, we will also have that there is no conserved energy, or?
Yeah, that's what we are going to discuss now. I'm going to discuss now. Yes, so far I just said that if I have a theory, matter theory, there are some rules to make it generally covariant by coupling it to by introducing metric and then promoting derivatives to covariant derivatives and adding the square root of minus g in the measure and so on, so that we get a general covariant action. So we just started from the matter action, we made it generally covariant, and from that we derived a conserved T mu nu for the matter. Now, of course, Einstein theory says that there is dynamics in the metric. So the same way that in the case of electromagnetism, we have an action just for a mu, which is the Maxwell action. What is -1/4 f mu nu squared. Similarly here, we can add a term to the action which only depends on the metric and not on the matter field. And that's exactly what we are going to discuss next. To talk about a piece of the action which only depends on the matter fields. And that piece is called the Einstein-Hilbert action, or it will become the Einstein-Hilbert action under some assumptions. So the full action depends on the matter fields that I generally call them psi. So this is a collection of all matter fields and the metric, and we decompose it into a matter action that depends on psi and g mu nu, plus a piece that only depends on the metric. So far we discussed the matter part of the action, but in principle, so this, what was the condition for constructing this? The condition for constructing this piece was that it's just we start from the original matter action and do the minimal thing to make it generally covariant. But then to that we can, and if we want to obtain the Einstein theory of gravity, the Einstein equation, to that we have to add a piece that also depends on the metric. So how do we construct that action? Let me put some G here. So this is the gravitational part of the action. The gravitational part of the action, again, the rules are the same in the sense that I am writing d4x square root of minus g, and then a scalar that depends on the metric. Now, what are the candidates for these scalars? So this L of g mu nu, it can be just a constant, which is called a cosmological constant. And then the next term that the next scalar quantity that I can construct out of the action, out of the metric and its derivatives is is the Richie scalar, which has two derivatives of the metric. So some coefficient C times Richie scalar, and then we can have terms with more derivatives, terms with more than two derivatives. So this first term is called cosmological constant. It is sometimes it is common to put the cosmological constant inside the matter action. In principle, there could be a constant coming from the matter action. And also, I also like to do that. So I would eliminate this cosmological constant. It could be in there. So it would be in the matter thing. Moreover, I guess for now we don't care about it. In the cosmology part of the course, then we will discuss it more. But now we are talking about asymptotically flat spacetimes mostly. And in that case, the cosmological constant has to be 0. Okay, then we will be left with these two derivative terms. And okay, I should say that this higher derivative terms. So this R, if you remember, Richie scalar is constructed out of the Riemann. So we have Riemann, which is a tensor R mu nu alpha beta, and it has the following structure, right? It has the derivative of gamma plus gamma gamma, where gamma itself is like the derivative of the metric. So therefore, Riemann, since it has this structure, it's a two derivative term. So it is of order, has two derivatives acting on the metric. And then we have the Richie tensor, which is R mu nu, and is obtained by contraction of the indices of Riemann. And then finally, we have Richie scalar. And as you see, these contractions do not change the number of derivatives. So Richie scalar also has two derivatives. Now this action, if I only write this term, then it is called the Einstein-Hilbert action. So as Einstein-Hilbert, and then for that coefficient C, I make a particular choice, and that choice has been made to match, for instance, the Newtonian limit, correct? So if I choose that C to be 1/16 pi g, then this will be the Einstein-Hilbert action. And now we can derive this full action with respect to metric. So if we take, well, let me first say that the derivation of, let me first say that if I take, if I vary the Einstein-Hilbert action with respect to the metric, then what I'm going to get is 1/8 pi g R mu nu minus 1/2 G mu nu R, which is nothing but 1/8 pi g times the Einstein tensor. Now, if we also vary, now therefore if we vary the total action with respect to G mu nu, let's also put this 2/the square root of minus g, and that whole thing, if you remember my definition of the energy momentum tensor, this variation gives me 1/8 pi g times G mu nu, the Einstein tensor from the Einstein-Hilbert part. And then it gives me the matter energy momentum tensor minus the matter energy momentum tensor. At this whole thing, I have to set it to 0. So as usual, we derive the equation of motion. In Einstein theory, the metric is not a dynamical field. So we also vary with respect to metric and set that to 0 to find the equation of motion corresponding for the metric. And that equation of motion for the metric is the Einstein equation. So this is the Einstein. Yeah, so okay, perhaps we should discuss the conserve energy in the next section. But yeah, starting from here, then we can find a candidate for the conserved energy in asymptotically flat spacetime, which will be the subject of next section. Any questions? So this material that I talked about in this section, they are mostly from 2 lectures of my older lecture notes, 2020 lecture notes. Actually, let me tell you which sections. So these are so there are 2 sections, section 10 and 11 on nonlinear gravity in my 2020 lecture notes. You know, everything that I said is more or less everything that I say can be found